everyone, my name is Jil Shah and today we're going to learn about Virial theorem and its application. Now, this is a very important theorem for all the physics undergrads as well as master's level students, but I'm going to keep it simple so everybody can understand this. Alright, so we're going to go through the history of the Virial theorem, the nature of the theorem, its importance, derivation, and applications, and then we'll sum it up. Alright, so history of the theorem. The word virial comes from vis, which is a Latin word for force or energy. Now, the technical definition was given in 1870 by Rudolf Clausius. Now, this guy also gave the concept of entropy, which is also the second law of thermodynamics, and he had a major contribution to kinetic theory of gases and thermodynamics in general. So he gave the technical definition of the theorem. And then later in 18th century, after a decade or so, the theorem was developed and generalized by many scientists who used the theorem for their own research work. And because virial theorem is a very generic theorem and it has numerous applications in all the physics areas, like it's not limited to one physics area, so that's why the theorem became popular with different findings of all these scientists. Now, Fritz Zwicky used the virial theorem to deduce the existence of dark matter for the very first time. So this theorem is quite useful in general. Now, the nature of the theorem, like what is the theorem, what does it tell us? So virial theorem relates the average over the total kinetic energy to the total potential energy for a system of n bodies. We can also say that virial theorem relates the average of mechanical quantities, and it is applicable to all stable systems, classical and quantum, as I just mentioned, that it is not limited to any one physics branch. And now astrophysics is one sub-branch of physics which has used or has taken advantage of this theorem in a very significant way, because this theorem has a huge significance for the understanding of the formation and evolution of stellar systems, and which we're going to see in a bit. Now, quantum systems also obey the virial theorem. Is a proof given by this guy called Fock. Okay, the mathematical representation of the theorem, which gives us this: the average of kinetic energy is equal to minus 1/2 of average of this quantity. Now, this is also known as the virial term, or the virial of Clausius, because the name given by the scientist who gave the technical definition. Now, Ri is the position vector for a system of n particles, and Fi is the force acting on the particles for a system of n bodies. So this theorem cannot be applied to a system of one body or a two body, three body. It is for n bodies, which we can say for infinitely large number of particles. So for that system, we can apply the virial theorem, and the system also has to be stable. Okay, so for conservative systems, which means that the work done is zero, the theorem takes the form of something like this expression given here, which is the average of kinetic energy to the average of potential energy, and this given by n plus 1 by 2. Now, n can have different values. When n is minus 2, it is called Kepler potential, but we are not going to go in detail into this. So for conservative systems, the virial theorem has this form, and K and V, as mentioned, are the kinetic and potential energies of the system. Now we're going to go through the quick derivation so nobody sleeps. We'll assume a system of n bodies with position vectors r and force Fi acting on the particles, and this is Newton's law, which is change in momentum per unit time equal to the external force applied. So we have taken a system of n bodies here. Now we're going to define a quantity S, which is the summation of all the momentum of the particle with the position vectors of all the particles. Now, this quantity that we have just assumed here or derived defined here comes from the moment of inertia, which is I equal to mr square, and it means that uh, with respect to the origin, a moment of inertia is the distribution of all the particles of the system, and is given by I equal to mr square. Now, when we're gonna differentiate it, we're gonna get this quantity. Okay, so now we are gonna do the time derivative of s quantity that we have just defined here. So that would be ds by dt equal to, this is simple derivative, so it would be pi dot into ri plus ri dot into pi. Again, nothing difficult there. Okay, now for the second term here, which is dr by dt equal to velocity, as we all know. So, and momentum equal to m into v. So for the second term, it becomes velocity into mv. So that becomes mv square, and then we multiply and divide by 2. So we get twice the total kinetic energy, because this is 2 into half mv square. And here kinetic energy is defined as T. So 2T, which is the kinetic energy. And the first term, this one, so dp by dt, as we have mentioned, it's force, and this is position vector. So this term becomes ri dot f, because we have written dp by dt as the force acting on the particles for system of n bodies. Okay, so the ds by dt, which is the time derivative of our defined quantity, becomes 2t plus this term, which is also known as the virial term. Now, we'll take the average rate of change of s over a time interval tau. Now, as I said, that this virial theorem is generalizes and relates various mechanical quantities for a system of n particles. So we have to take the average of this quantity that we have just found. So we're gonna take this brackets means average of the quantity. So we're gonna take 1 by average of this, which would be 1 by tau integration 0 to tau ds by dt dt. Now, this would give us 2t plus the virial of Clausius term. So we have just written the average of this is average of this plus this. So we have just written the same thing here. And now we're going to equate these equations, this average time interval term on the right hand side, and this average of the kinetic energy plus the virial term. So when we equate this, now using the fundamental theorem of calculus, we can write this, which is 1 by tau into s by tau minus s of tau minus s of 0. We are just putting the limits there. So hence, for periodic systems and for non-periodic systems, this term, which is the RHS, it becomes 0. Now, if the system is periodic, which means that and we take the repeated values of tau, because tau is going to repeat if the system is periodic, and that means s of tau minus s of 0 becomes 0 because of the repeated values of tau. So if this is 0, then 0 into 1 by tau becomes 0. So RHS is 0 for a periodic system. Now if the system is non-periodic, again we're gonna assume that if we take tau to be a very large quantity. Now tau is the time interval. So when tau is very large, that means that we're gonna observe the system of n particles for a very long period of time. So if we do that, then the inverse of this, which means this quantity, becomes very small, and as a result this big term becomes 0. This term here is also a mathematical representation of ergodic hypothesis that we're gonna look in a bit. So in both the cases, RHS becomes 0, and thus we get the average of kinetic energy equal to minus 1/2 of this term, which is also known as the virial of clauses term. So this is just I've just sent the 2 in the denominator, and this term has gone to the right hand side because this is 0. So that's just playing around with the terms. So average of kinetic energy, which is T here, and is equal to minus 1/2 of average of this term Ri dot Fi, which is the mathematical representation of the virial theorem.